All right, welcome everyone to our first Friday seminar. And so the Friday seminars are alternating between IS and Princeton University roughly. And so today we are very happy to have Sahand here. And yeah, I should also say that mostly in the fall we'll have our new postdocs giving us talks, and so that will be our focus. But yeah, today we're starting off with Sahand, and he will tell us about non-invertible symmetries and their representation. Take it away.
Hey, hello everyone. Thank you for inviting me, and thank you for coming here. So I thought that the purpose of this seminar is to other people get familiar with what we are working on. So because of that, in the first half of the talk, I will try to give a review mostly of non-invertible symmetries and some of the results. And on the second part, I will give a more technical talk, become more technical, and I'll give you some new results. So the first part is just review and some old results, which is based on this paper. And the second part is about representations of non-invertible symmetries for derive selection rules, and I derive asymptotic density formulas. I will start later. And this is on a more recent work for a month ago with Ingsom Lin at Harvard, Masaki Okada, a student at Japan, myself, and Yudi Tachikawa. Okay. So let me begin. So in the first part, I want to give a modern definition of global symmetries. And so I'll start with Noether theorem. Noether theorem tells us that for given any global symmetry, we have a conserved charge, or more precisely, given any continuous symmetry, we have a conserved current and a conserved charge. Right? So we could, given symmetry, we have the conserved current, and we can define a conserved charge Q, which we can define it by integrating J0 over the whole space. So in my notation, D is a space-time dimension. So this is like a space. So sigma is a spatial slice. I integrate J0 and define a conserved charge, right? And more importantly, we also have a unitary operator. So we could define U of alpha of sigma, which is just e to the I alpha Q of sigma, by exponentiating the charge. And this is a unitary operator which acts on the Hilbert space. And because this is a symmetry, this is conserved, it means that this operator commutes with the Hamiltonian. So this will translate to this fact that this commutes with Hamiltonian. So we have a symmetry, right? But what we can do more is that we can define and do a nice trick and define a D-1 form out of this J. So I just use this tensor to define this J, which is a D-1 form. It's not clear. Is it visible? Is it big enough? Okay. So I define this D-1 form, and it's good because it allows me to define this U of alpha on any coordination 1 sigma. So I just simply integrate this D-1 form over any sigma. And this conservation equation becomes the fact that J is a closed form. And because J is a closed form by Stokes' theorem, if I deform sigma a little bit, this doesn't change. So we will say that this operator, U of alpha, is a topological operator, meaning its dependence on sigma is only through its topology. So if I deform sigma a little bit, as long as I don't cross any operator insertion in my space-time, I get the same answer, right? So this is topological. So then it gives us a modern definition of global symmetry. She says that global symmetry equivalent to topological operator or defect. I will explain what I mean by defect and operator. This is from a paper by Gaiotto, Nari, Capusti, and Villas in 2014. Sorry. Okay. So now, let me. So I should mention that I'm using the term operator and defect interchangeably. So when I have this U alpha, when sigma is space-like, this is just literally an operator which acts on the Hilbert space. So I use the term operator. But when sigma is time-like, meaning it intersects the space, then I have to quantize my theory in the presence of sigma. So I get a defect. So this imposes twisted boundary condition for me. So, but in a Lorentz invariant theory, whenever I have a defect, I could just look at it from another angle and view it as an operator. But as an operator, it's a more restrictive operator because the defect has to satisfy a very constrained normalization condition. But I'm going to use these two for interchange. But I want to mention that this is not just a language, this is not just a new term. Every notion that we know about global symmetry can be translated to the language of topological defects. So I prepared here a small dictionary that stores some of these relations that we know about symmetries and language of topological defects. So in this talk, I'm going to mostly focus on 1 plus 1 dimension. And so because sigma was codimension 1, initially it was correspond to space. So in 1 plus 1 is just a line. So in 2 dimension, 2 space-time dimension, a symmetry is just a topological line operator or line defect. Okay, and these are the relation that we know. So for symmetry, we know that we can act on local operators, and in this language is just having a local operator insertion and wrapping it with some topological line, which is labeled by some G. This line is topological. I could just shrink it and get a new operator, and this is the action of the symmetry on local operator. Then I can define G twisted. Okay, I could define G twisted boundary condition. I don't have a space over there, and this corresponds to inserting the defect, as I said before, along space. When I have this defect along space, when I quantize my theory, whenever I cross it on a circle, for example, if it's Z2, I get Z2 twisted boundary condition. So when it's on space, it gives me twisted boundary condition. Then I have a group law for symmetry. I multiply 2 unitary operator. I get another one, which is labeled by G times G prime. This is the group law. And it corresponds to the fusion of these lines. So I could put 2 of these lines near each other. And because they're topological, I could just view it as another line, given that there's nothing operator insertion in between. The fusion is group law. I could also couple my theory to background gauge field. Coupling to background gauge field corresponds to inserting a network or mesh of these defects into my spacetime. So basically, if I have some gauge field, I have to insert this network on the Poincare dual. So this is some 1 form, and the Poincare dual would be 1 form, would be something in homology, for example.
For continuous symmetry.
Okay. So yeah, that's a good question. So here I'm focusing on discrete symmetries. Yeah, because I could, this is more precisely correspond to coupling to flat background gauge field. This time, yeah. And for discrete symmetry, we can only couple them in a continuum to a flat background gauge field. I could also gauge them. Gauging, it means that I make the gauge field dynamical. So it means that I just sum over all these insertions. But there might be obstruction to gauging, and that's called Tooth anomaly. And Tooth anomaly, it just means this pictorial relation. That when I do this crossing move locally, if I'm not able to do it, it means that more precisely, if this network has a more dependence, it not only depends on homology of this network, but it actually depends on actual topology, then I have an obstruction to summing over all these insertions because it depends on the detail. And then this is not equal to this is the Tooth anomaly. So generally there is a U1 phase, which is some Trico cycle, which captures the Tooth anomaly. Okay. Is there any question so far?
So G1, G2 was defined by the group law.
Here?
Yeah.
Yeah, that's true. So in this case, the only non-trivial junction exists is just between G1, G2 and G1, G2. So if I put something else, which is not G1, G2, there is no junction that I could put here. So it wouldn't exist.
Yeah. I'm a little confused how it could not be true. So because G1, G2 is just the product of the two, right? The group composition law.
No, I'm saying if this wasn't G1, G2, if I put like something else, then this junction wouldn't exist. Maybe I didn't understand the question. I'm saying that the only correct label for this line is just G1, G2 because of this relation.
Yeah, I understand that. And the fact that you can go to G3, G4 means that G1 and G2 is equal.
Oh, yeah, sorry, that's your question. That's true. Yeah, yeah, exactly. If it's not a million, then this is zero. Both hand sides are zero. That's right. Yeah, I have to assume that G1, G2 equals G4, G3.
Okay, fine. But then the one, like, understand how it could be different from the other diagram.
Oh, you're saying how could it be that these are not the same? They could differ by phase.
Maybe explain for the junction is because it's not
Yeah,
clear
yeah.
there is a junction.
Yeah, so I'm saying that from this picture, you know, I have G1, G and G prime coming in, but then consider this, right? But this part, as I said, is equal to this, right?
Right.
So I could just exchange this with G prime. I get a junction between G prime and G prime. And in this theory, because only this junction exists, right? So this is the junction. All I'm saying here is that sometimes these two pictures could differ by phase when the theory is anomalous. So I could give you an example of Z2 case. So for the Z2 case, let's put the theory on first. Let's do the Z2 case. So there are two things that I could do. I could put a line here, or I could do this. Right? So I'm just, this is just that two picture, but I have the trivial line in the middle. So no one said that this has to be equal. In fact, I'm assuming that this is a Z2 line. This is eta, such that eta times eta is 1. So in general, one could find that this is usually can be related by minus and alpha give you the anomaly. So yes.
There's a problem with your presentation because you haven't defined these pictures precisely enough for that statement of the phase to be meaningful.
Right.
You've only defined these pictures like classical pictures. So on neither the left nor the right is the sign clear from anything you've said.
Right.
To make it accurate, you have to give a much more detailed recipe about what your pictures are supposed to mean. And that recipe will not have the symmetry of the picture you're drawing. Because
yeah, I understand. So yeah, it's 100% true. So when I explain the junction, so there is a choice of there is a vector space at this junction. So there is a choice of vector that I could put at this junction. And that statement is that if you fix a basis for all of these junction vector spaces, then you cannot pick any basis such that these two pictures are equal.
I think that's still not sufficiently precise. But go ahead.
Let me see if I can.
When there's an anomaly, it precisely means that the picture is ambiguous. Therefore, to define the picture for more information.
Yeah,
I suspect if you're going to define the picture precisely, you pick a Hamiltonian picture. I don't know if that's true.
Yeah.
That would be one way to do it. But then you'd be introducing a preferred time direction that wasn't part of the picture. That would show that to define, with that approach, you'd have to end up saying that to define the picture enough precisely, that the two sides have definite signs, and you can say they disagree, requires information that wasn't present.
Yeah. Would that, if I, so as I said, if I label the junctions with X and Y, then I completely specify each picture. So that picture by itself, I agree it's ambiguous because of the anomaly, but once I pick some junction vector at each junction, then it's a well-defined picture.
I don't think so. I think the difference, I think there's additional input, a Hamiltonian or something that you would supply to define the pictures precisely enough that you can say they're unequal.
Okay, maybe I'll ask him later because I don't know. I thought that only, yeah.
Otherwise, you'd be able to learn based on nothing whether the theory was anomalous.
So I'm saying that just the fact that these lines have this crossing give me, and this is information about, you know, I can deduce this information from the Hamiltonian or the Lagrangian. I can deduce that these lines have this non-trivial crossing, then I find that it's anomalous. So for example, this picture here, I'm not using any junction.
This picture is on the torus, right?
Yeah, that's right. I'm putting torus, I'm not using any junction.
They're topologically equivalent. You just have an unknot on the torus. So since they're topologically equivalent, if you say they differ by sign, there's some information that isn't present in the topology.
I think they are not topologically equivalent. So if I use the state operator correspondence, one of them is clockwise, the other one is counterclockwise. And this will measure the spin modulo 4. So if these states in the twisted sector has spin 1/4 or 3,
Z2.
yeah, this line is Z2.
Okay, so all you have is a circle that's contractible inside the torus. And the circle is labeled by the non-trivial element of Z2.
Is it contractible?
Yes. The lower one could move down. Oh, sorry. Oh, well, if not contractible, they're still topologically equivalent.
But I'm saying in the state operator correspondence, this is 2π rotation, this is minus 2π rotation. So they differ by 4π rotation. So if the spin of this line, if the spin of this line is I
don't want to interrupt you more, but I really think that there's more data. I think for them to be anomalous, they have to each depend on something you haven't said.
You agree that these two pictures correspond to these two by the state operator correspondence?
I'm not sure.
Okay, sure.
Are these pictures supposed to apply in this case that we integrate some operator?
Yes.
Do I still get the phase? Can I still possibly get the phase in that case?
I believe so. That just gives, I mean, the concrete theory for this would be U1 level 2, which is anomalous, and you would get these phases.
They just join the diagrams at the point. And then
but the point is that exactly that this operation can introduce a sign.
So is it fair to say that the whole subtlety is that when you write U alpha as exponential of an integral of current, and you go to the quantum theory, then they haven't told us how to regularize the exponential.
So this is a way of defining topological defects, and maybe you're right, but I'm using this definition. I just define symmetry by topological lines.
Yeah, classically, yes, but then you have to promote it to a quantum operator.
So I'm assuming that I already have some quantum operator here. All I'm saying is that these lines could sometimes, there might be a minus sign. And when there is a minus sign, the theory is anomalous. So this anomaly is a property of these topological lines and their set of junctions. So I'm assuming that given the theory, I could do some computation, non-trivial computation, to deduce these numbers. So here there would be, in general, there would be F moves, like F moves of Moore Cyber, the fusion data, which in RCFT, we know that we could compute them by looking at the RCFT data. But this is some non-trivial data. I didn't tell you how to compute them.
Do these wrap the same cycle on the torus or the two different cycles?
So this is A plus B cycle, this is A minus B cycle. So modulo 2, these are the same cycles. Modulo 2. And the symmetry is Z2. So you might say that, okay, this is okay. But actually, for the anomalous case, you have to care about this modulo 4. Because when it's anomalous, these ultimately it relates to the spin-off operator in the Z2 twisted sector, and they could have a spin quarter. And I get this non-trivial thing. Yeah, maybe there is something that I don't understand. I don't know. I cannot answer it real time.
Just if I understand. So if this J was, let's say, a light moving current, and just U1 Boltzmann theory. And in this case, we expect an anomaly. Do something.
Yeah, that's right. You could take this Z2 subgroup. The whole U1 left moving is anomalous. Yeah. So I would say the discrete subgroup is also anomalous.
We're only talking about global anomalies, right? Not local ones.
Why do you mean local global?
There's only like an anomaly, the anomaly polynomial branch.
Oh, you mean discrete versus, okay, the perturbative versus non-perturbative. Yeah, these are discrete, these are non-perturbative. Yeah.
So that's would answer one question. Because you're
Okay, so in that case, is there, I mean, this anomaly doesn't have a manifestation moving these lines? Just the standard perturbative anomaly.
they're not topological.
Why they are topological? They're always topological. They are labeled by some discrete label by the level of the transaction.
There's a local mixed anomaly between the two U1s and the 3+1.
I thought that we were talking about the left mover, which had anomalous, just the U1 left symmetry.
Okay, so that U1 left symmetry gives some symmetry of this kind.
Yeah, here I'm talking about discrete one, but yeah, if you want to talk about the U1, yeah, that's also anomalous. I don't know how to capture those kind of moves precisely for continuous one, because for continuous one, we could just compute the 2-point function there. The contact terms.
Yeah, I understand that in terms of the currents, the pressures of currents. But
as I said, okay, let me be more precise. So in U1, so in SU2 level 1, for the self-dual boson, as I said, this is just basically the spin of the operator in the twisted sector. And we have the full spectrum of SU2 level 1. It has 2 primaries. And if you go to the twisted sector, it has a 1/4 operator. And it has operator with this dimension. And because the spin is a quarter, it's clear that these are related by minus. You agree? Because this is 2 pi rotation, this is minus 2 pi rotation. And this is the spectrum of a SU2 level 1. So it's clear, tell me.
I don't know what this picture means.
Oh, this one?
Yeah.
Okay, I have so okay. In SU2 level 1, if you go to the Z2 twisted sector, there is this primary with this scaling dimension.
The blue line is what implements the Z2 twist.
Right, exactly. So this is the Z2 line, eta, which implements the Z2 symmetry of SU2 level 1. It's comes with the parallel algebra. And because I'm going to the twisted sector, so by using state operator correspondence, this operator is at the end of this line, right? So I'm saying that this picture, if I do radial quantization, it corresponds to this, and this picture corresponds to this. So here I'm doing 2 pi. So these 2 pictures are related by 4 pi rotation locally, and because the spin is a quarter, so I get a minus sign. Oh, I'm missing maybe a yes.
Just to make contact with what I was saying before, when you invoke the state operator correspondence, you are regarding the vertical direction as time.
Yes.
So that's the additional structure you use to detect the pictures meaning.
Oh.
All I said before was that additional structure they weren't meaningful. And now you told us which additional structure you're introducing. The cycles A plus B and A minus B are equivalent under pi 4 rotation of the torus. So
I see. Okay.
it takes additional structure to distinguish
Yes.
A plus B from A minus B.
Okay, thanks. Is this clear or?
I think that is clear. I don't know how it's related to the torus, but anyway, we can continue.
Okay, by state operator correspondence, I'm saying that universally tells us that in the Z2 twisted sector, the operator should have spin a quarter. And it tells us that everything that is here, you know, they're related by minus sign. So the whole partition function on torus is related by minus sign.
You also would have, I believe you would have said that the picture on the left, not comparing to the right, just interpreting the picture on the left with 2 different notions of time, you would have gotten opposite signs. Okay.
Yeah, I agree. There is some extra choice. Yeah, definitely. I see the point. Yeah. So yeah, and if I use junction, that would be related to some subtlety about these lines that are not exactly Z2 is not exactly related. So then the orientation would matter. So it's Z2, you naively think it's the same as its orientation reversal, but there is some kind of anomaly. So this line on its word volume has a time reversal anomaly, which doesn't allow you to identify with this orientation reversal. But I agree, yeah, there's some addition. Any other question? Okay, good. So now I have some dictionary about the notions about symmetries and topological lines. And now I want to just define generalized symmetries. The first one is just higher form symmetry. Higher form symmetry is a symmetry that acts on, instead of local operator, it acts on higher dimensional operator, like line operator, surface operator. So instead of being generated by codimension 1 operator, they are generated by codimension 2 topological operator, and so on. But in this talk, I'm not going to discuss biform symmetry. So let me not mention that. I just mentioned non-invertible symmetry. The non-invertible symmetry. These correspond to defects. So topological defect U without an inverse. What do I mean? So when I do this fusion, so when I took two lines, let's say I take U and I have another, it's inverse. If it's invertible, when I fuse them, I should get the identity line. When it's non-invertible, is not the case. And so more generally, if you have two lines, let's say 2I, J, if I put them parallel to each other, instead of just one line, a group law multiplication, I get sum of lines. So I get sum over NIJK, with sum of the UK. As for a group law, I just get one single term on the right hand side. So we have some fusion algebra here. So, but these numbers are non-negative integers. Ultimately, they are dimension of some vector spaces. That's why they are non-negative integers. They are the dimension of these junction vector spaces. But I don't want to get into detail, but yeah. So there is an equivalence between this number and the junction. So that's the first thing. So the group law becomes this fusion rule. The second thing is about the anomaly. So I could about what about this structure? So this structure turns into a crossing relation. I guess almost similar looking equation, and on the right hand side we have a matrix. Like each of these numbers are a 2x2 matrix. You have UI, UJ, UJ, UL, UI, UL with some choice of orientation. So this is UN, UN. So this is also sometimes called the 6J symbols, or the F matrices of Moore-Cipher from the RCFT data. And so see that for non-invertible symmetry, so for ordinary symmetry, the structure that we have is a group, and it's two anomaly. But here, all the data of this topological line is this bunch of fusion coefficients, a bunch of non-negative integers, plus these F matrices, which satisfy a pentagon equation. So I have just NIJK plus these 6J symbols. And mathematically, mathematicians call this data a fusion category. But as physicists, we just can work with these two data. These are this data of this symmetry, which captures both the symmetry, the group law, and the anomaly. And it's nice because it's been proven that these are, if you want to find all consistent solution to this, it's rigid. So these structure don't admit continuous deformation. It means that during the RG flow, you have some kind of anomaly matching, because if you treat this as an anomaly, this cannot change. This doesn't admit a continuous deformation. So from UV and IR, they should be the same. It's called Occhiano rigidity in this mathematics.
So would it be accurate to say that your invertible lines or invertible symmetries are, so you have some category, and in your category you have basis of simple objects?
Yes.
And so those are your invertible symmetries, and then the non-invertibles are just a general object in the category.
No. So I'm only considering simple objects. So some of these simple objects might be invertible, some of them will be non-invertible. When I say non-invertible, I should say possibly non-invertible. So not all of them are non-invertible. You know, I have a bunch of lines, set of lines. Some of them are invertible, some of them are not invertible. But all of them are simple lines that they're not sum of three other lines. Otherwise, I wouldn't discuss that. So when I write these things, these are all simple objects or simple lines.
Okay, your category doesn't necessarily have a basis of simple objects.
Yeah, it's a particular representation in the basis set. So, for example, when I define lines as exponentiating J, I don't take two sums. So when I sum them, this wouldn't be simple. I won't work with these objects. I have an object which is just a single one.
Can you give a simple example of an invertible?
Okay, yeah, I will give. So before giving the concrete example, let me tell you that the most important examples are just 2D RCFT or 2D G-level KWZW models. I will get back to it, but for now, I'll give you a very concrete example, the simplest example, which is Ising CFT. So Ising CFT has 3 primaries. Trivial, the energy operator with this conformal dimension, and the spin operator, right? It turns out that the Ising CFT also have 3 topological lines with the same fusion rule as this. So the identity, it has a Z2 line and a non-invertible line. So there exists a non-invertible topological line, let me call this N, which implements the Kramer's Vanier self-duality of the theory. But I don't want to get to that story. So there is some non-invertible N. And what's the fusion rule? So it also has a Z2 line, which I call eta. So the full fusion rule is that eta times eta is 1 because that's Z2. So this tells us that this, so eta times n equals n times eta equals n, but n times n is 1 plus eta. So it's clear that this is non-invertible, you cannot cancel it, and n is same as this orientation reversal, so it's self-dual. Okay, and this is the same fusion rule as Ising. Is that a question?
So if I understand correctly, your definition for something to be non-invertible symmetry is that there are some lines for which there's no way to combine them with another line, so that on this right-hand side, you only get the identity.
Exactly, exactly.
But it can contain the identity in general. Yes, also something else.
If you fuse it with this orientation reversal, it would always include the identity.
Okay.
But if it's non-invertible, it also includes other lines. Okay, so now let me tell you about this action. How it acts. So eta just acts as ordinary Z2. And we know that this is even and this is odd under the Z2 symmetry. But the action of the non-invertible line is a little bit more interesting. So the way that it acts on energy operator. So let's say I have this non-invertible line and I push it through epsilon. I just get a minus sign. However, when I have the spin operator at point X, if I push this non-invertible line through it, I don't get the local operator. I get the disorder operator, mu. So these have the same scaling dimension as sigma, 1/16, 1/16. But it's attached, it's not local because it's attached to this eta line, to this Z2 line. So by using state operator correspondence, this is the Z2 twisted sector. So the most important property of this non-invertible line is that they can map local operator into an operator like this, which I call the defect operator. So such a thing, I call it a defect operator. I could sometimes call disorder operator or twist field. Sometimes people use these names. But basically, these are operators which are attached to some line or on the twisted sector, like in SU2 level 1, WZW example that I tell you. Is this clear?
Yeah, I had a question. So sigma and mu are mutually non-local, we know that, but isn't it a convention somehow? Which one is the local?
Okay, very good question. So the fact that they are non-local is exactly because of this line. And you said that is there a convention? So in this theory, I could do an operation, which is called, I could gauge this Z2 symmetry. And it's known that Ising model at the critical Ising model, the CFT, it's self-dual under gauging Z2. So when you do gauge the Z2, whatever you do, you just, this line no longer is attached to eta, but because this is not gauging variance, now you attach it to a Wilson line. And then it gives isomorphism between the theory before and after gauging. And it's very important because usually non-invertible symmetry arises from self-duality when you have a theory which is dual under gauging a discrete symmetry.
Can I understand the picture you drew at the end there? Am I supposed to really think there's the blue line is an N? What is your blue line?
Okay, so if I want to draw it more precisely, I have such a thing. So I don't touch its endpoints. I'm doing a move locally. So I have this line N, and I locally.
But are you saying that when you drag the line N through the point, there's a new line, there's a juncture there added?
Exactly, there's something that appears. This D2 line that appears. Where for invertible one, it won't appear. It just acts invertible.
Well, this uses the NN eta junction.
Exactly. Yeah. And so from this, there's an important lesson that is pretty general.
You could also have examples, right, where you don't have you can have a non-invertible line where you do not have this.
Yeah. It's not always like that.
Yeah.
But
in this example, right, you can just project, let's say, to the spin operator. That's non-invertible.
Yeah, but that's another action. So the whole point of my talk in the second part would be the distinguishing between these two kind of actions. So I have one action defined there by wrapping a local operator with a line, and I have this another action. I just don't close the line. And yes, this contains more information than that data. That data projects out some state to zero, so it doesn't have all the information.
What happens if you take the N line around the sigma?
It's just zero. Because there is nothing in the untwisted sector. You only have something non-zero in the twisted sector. It turns out, and that's what I want to say, is that invertible symmetry it has an action that can map a local operator into a non-local or defect operator, and vice versa. So let me say what is an equation for this one. So there is a operator U of M, which not only acts on, let's say H, I'm using state operator correspondence. Let's say H is just the circular Hilbert space of the CFT, but I also have operator in the Z2 twisted sector, and they correspond to this twisted Hilbert space by this line eta. So H of eta is just a twisted Hilbert space. So I have an operator which is a map from this extended, this bigger Hilbert space to itself. This is a thing which for invertible symmetry only acts on ordinary Hilbert space. But here I have a more general action. An important point is that in this particular case, this is unitary. Even though I started with a non-invertible symmetry, this operator is unitary. And how it acts, it sends epsilon to minus epsilon. It sends sigma to mu and mu to sigma. So it's like kind of act like Z2. And there's a more general story. So in general, for any non-invertible lines, I could construct such a map which is invertible. I can construct a map from H, which I twisted by this line, eta times eta bar to eta bar times eta. Sorry, n times n bar times n. But if n were invertible, this would be just identity. So I just get usual unitary operator from H to H. So this is a more general thing that
notation means that you take all the lines. So you take n times n bar, and then that would be a sum of lanes.
Yes.
And then you take the h's, the route to the h's.
Yeah, exactly. Then I expand it. Yeah, I should have said that. Yeah, I expand these Hilbert spaces. So I have a bunch of Hilbert spaces. I have a direct sum of all of them. And in picture is corresponding. So here I just get only one term. I just get something in the twisted sector in here. But sometimes you get something here, like for the epsilon. Epsilon is here, goes to here, but sigma is here, goes to here.
What's the definition of n bar?
Oh, it's okay. So all of these lines are oriented. I just change the orientation, which for the invertible case becomes like the conjugate or the inverse. Yeah. Any other question? Okay. I don't have to watch. So in the second part, let me just, to motivate the second part, I want to talk about a possible relation with people interested in quantum gravity, that these generalized symmetries and non-invertible symmetries appear. We know that there is a law in quantum gravity that there is no global symmetry. In other words, all symmetries must be gauged in the theory of quantum gravity. And this is related to the completeness hypothesis. It says that given any gauge group G, all the representations should appear in the spectrum. But recently, there has been even a more stronger statement that given a G, there is given a gauge group G, people indicated that there should be a universal formula that tells us how many times a given representation should appear in the spectrum. But inside, I'm going to just focus on the particular QFT aspects of this universal formula in the context of 1 plus 1D CF. So when G is a group symmetry, such a formula has been derived in the literature. In 20, and it says that in a 1 plus 1D CFT with a discrete symmetry G, so asymptotic density of states in representation R is proportional to the dimension of the representation square. So it's a finer version of the Cardy formula. For the Cardy formula, we have a symptotic relation for the symptotic density of states, but then it makes it finer, and it says that when you take the very high temperature, the given representation R should appear dim R squared with this proportionality factor. What I'm going to do today, I'm going to generalize this result when I have a finite non-invertible symmetry. Is it clear? So this is the formula. Any question about the formula? Okay. So what I have to do to answer this question, I have to first generalize the notion of representation. I have to tell you what do I mean for a representation of non-invertible symmetry. Once I have defined, I could give you a formula. And let me just write the formula. So the symptotic density of states in a representation, we call it mu. I have to define what I mean by this. And I slightly generalize it, and I can derive a formula for the density of states in representation A in a given twisted sector. So I could also twist it with an element A. So if you only want to care about the local operator or just the ordinary Hilbert space, you could just set A to be 0. But A is some elements in the non-invertible symmetry, some of these non-invertible symmetry. So what the formula is? So first, this is going to be some non-negative integer that I'm going to explain what it is. So this is some integer like this. This is going to be some fusion coefficient. I will explain. And this becomes the quantum dimension of that representation. I also have to explain. Quantum dimension of mu. And it's interesting that in the special case where it's invertible, both of these numbers are equal to dim R. So I get the same formula. This is the thing that I try to maybe motivate or derive. Depends on that. Oh, I should have deleted that. So, as I said, I have to explain what I mean by representation of a symmetry, non-invertible symmetry. And what I really have to tell you is that what is the action of a non-invertible symmetry, how a non-invertible symmetry acts. So you could say that I just would take this naive action. So you could say that the fusion algebra acts. The fusion algebra action, which I just take O, map it to this. And so there's a fusion algebra, finite dimensional algebra, which act, and I could just take its representation. I could organize my local operator into representation of this fusion algebra. This is what we do for the group case, right? Because we could take a representation of the group or its algebra, doesn't matter, right? But one drawback of this is that usually when we have a fusion representation, we have a notion of tensor product. So if I give you a composite operator, so let's say I have O1, a local operator in representation R1 and O2 in representation R2, and I insert two of them at two different points space-time, and I want to ask, what is the representation of these composite operators? In representation theory, we know that there is a notion of tensor product, and I know how this composite operator transforms the representation. Now I could use this fact to derive selection rules on correlation function, let's say endpoint function. I just take the n operators, I multiply its representation. If the identity representation does not appear, I could say that this correlation function should be 0, right? Because the vacuum is. But if I don't have this rule, I cannot do it. And it turns out the fusion algebra does not have enough information to tell us, to give a way of, canonical way of answering different representation. But this more general action that I deleted, like that action, gives me this information. This is sometimes called the Lasso Action, which is the most important property of non-invertible symmetry. So it tells me that if I have a local operator O, I could not only wrap it with another line, I could also attach a tail here, B. Right? So this is a map from H to H.
So do you restrict to indeed to non-invertible operators to the same inverses and not like there, yeah?
Sorry,
so are you restricting to non-invertible operators here or also invertible back from H only to H, like not like the other two went to the twisted sector?
Yeah, here it goes to the twisted sector.
Yeah, but okay.
No, I'm saying that you could consider this action. If you do that, you get 0. But if you just consider this action, you get something else.
Okay.
So you have to consider all of them.
Okay.
And even more generally, you could also attach something here. So you could label this with C. And then you have to specify the choice of junction that you have to specify. And this gives a map from HC to HB. So I have a map from this twisted sector to this twisted sector. It might be 0, but some of them are non-zero. And it's very important for non-invertible symmetry. Some of them will be non-zero. Right? So I have this more general action, Lasso action. And I could just compose two of these actions. When I act, I could compose another one on the bigger super and so on. So they form an algebra. I could just take linear combination, I could multiply them, and so on. Right? And they form a finite dimensional algebra. So here the finite dimensional algebra is the fusion algebra, like the Berlin algebra. But here I have the finite dimensional algebra, which is known as the cube algebra in the mathematical literature. So I should say that here I'm using the notation where A, B, and C are the elements in the non-invertible symmetry that I denoted with big C, with capital C. So let's say C is the set of all these non-invertible symmetry, and this is known as the tube algebra. Yes.
The fusion algebra is commutative, the tube algebra is not.
Okay, good question. So here, if I take the Berlin algebra, it's commutative. But in my definition of non-invertible symmetry, I could also consider non-commutative fusion algebras. So I don't restrict to commutative. So both of them could be non-commutative. And it could be that this is commutative, this is non-commutative, as I said. But I'm taking more general case that both can be non-commutative. Any other question?
How is the right-hand side defined of this transformation? Don't you need to resolve the vertex? Yeah.
So I'm saying that you pick a junction, right? It could be two-dimensional junction. It could be a vector. Everything is topological. So you shrink it. At the end of the day, you're going to get a new operator.
But if it's an anomaly,
No, anomaly tells you that whatever you do, if you have two different pictures, these two pictures might be related by a face, but a given picture should have a unique answer. If I label all of my junctions with something, so I have a four-way junction, I'm labeling it. Yeah, maybe you said that I only have the basis in the trivalent junction, and I want to label this with that. I'm collectively calling it X, but yeah, if you mean that, yeah, you could do that. But I don't care about the details of what's going on here. I just call it X.
So by this being a representation, you mean that this assignment, this map respects the, if you wrap it around, okay, then it respects the whatever the fusion algebra you define for. Is that what you mean by representation? This being a representation of fusion algebra?
What I'm saying is that I have this, so I could consider these actions, and they formally form some algebra, which is a bigger algebra than the fusion algebra. So fusion algebra is a sub-algebra here, and I just take C and B equal to be 0. Now I consider this algebra and take its representation. I'm saying every operator, both in the untwisted or twisted sector, transform under some representation of this algebra. And this algebra is very nice, can allow me to derive asymptotic density formula and auto selection. Okay. Cool. Any other question? Now you could ask, okay, I'm defining something which is a bit scary. So algebra, what is the representation? Can I know what is the answer here? And in some special cases, I will give you the answer, but let me first give you the most general answer. So if I fix a non-invertible symmetry C, which could be like a Berlin symmetry, some diagonal or CFT, what is the representation of this algebra? It turns out that this corresponds to the anions in a 3D QFT. I will denote it with T of C, sometimes called derive here. So by anions, I mean just topological line operators or line defects. Okay, I'll explain what it is. So the claim is that there exists some TQFT in one higher dimension whose line operators labels the representation here. And I will give also a physical explanation why this is expected and it's not very helpful. So let me give you 3 facts about this TQFT in one higher dimension. So you could ask, when this symmetry is invertible, just ordinary group symmetry, what is this TQFT? Is this something familiar that we know? The answer is yes. So when C is invertible, I mean it's just given by group G, by discrete group G, and it's an anomaly. So let's say this is just a group G, this is an anomaly. Then TBC is just the G omega Diagonal-Witten theory. So this is just Diagonal-Witten TQFT. It means that it's a discrete G gauge theory with the action given by omega or a twist given by omega. Omega is a 3 cycle. Right? So this is a topological theory. It's a discrete gauge theory. In other words, this is a gauged SPT in 2 + 1 dimension. So this is a gauged SPT 2 + 1 associated to this. So we know that by anomaly matching, every theory, any QFT with some given anomaly, it corresponds to an invertible theory in one higher dimension, which is sometimes called the SPT. And I'm saying that take this theory, consider the SPT in the bulk. SPT is like a classical theory, it's invertible. All the Hilbert spaces is one-dimensional, but it has a G symmetry. Now, gauge the G symmetry in the bulk. When you gauge G, you get this theory. And this is supposed to be the intuition for the general case. It's basically the gauge SPT in one higher dimension. So the other comments is that this theory also has a lattice realization, known as the Levin-Venn stringnet model. And the other fact is that all TQFTs with the gapped boundary are this derive here. And gapped boundary will make an appearance.
Okay. Problem with notation. So when we think about this algebra, I thought maybe some algebra in the usual sense.
It's the usual sense, that's right, that's right.
By groups, and you would tell me, can I classify this algebra in terms of classification of discrete groups, for example?
Wait, I mean, so this is an algebra, but the classification algebra is, I'm not yet told you what is the properties of this algebra. If you just have usual algebra, the classification,
This is an algebra. This means some algebra where I just multiply things.
Yeah,
and so
yeah.
on. There you have some filtering, something that's more complicated. Right? That's where I'm good.
okay, that's right. So, okay, right, that's a good point. So there is not a one-to-one map. Given this algebra, I'm saying that you take reducible representation, they are labeled by the lines in the theory. But this algebra has more structure, which I haven't discussed yet, which gives more relation here, like the braiding between the anion and the fusion. I haven't spelled how to get from here to here, but I could give you the physical explanation. But I'm not saying that this is the equivalent.
Yeah, onions and that stuff suggests a braid group.
That's right.
So this looks like just much.
Yeah, it has more structure than just multiplication. It's an algebra equipped with more data, and those more data give you those extra things that you said. I'm not discussing that yet. But I will give you the physical appearance right now of this QFT, and I'll just give you like one piece of this mathematical operation.
What's the street version of Chern-Simons WEW?
Say again?
So so it looks very similar to Chern-Simons WEW. This thing that you.
Yeah. It's related. You mean when you have double and Chern-Simons in the bulk?
Yes.
Yeah, I will discuss that example. I have to rush because I have 5 minutes.
Yeah, I think we can go a bit over time.
Okay, not too much, but I will do maybe 5 minutes. Sorry. What is the physical interpretation of this QFT? So it relies on a single fact that any two-dimensional QFT that we call Q with symmetry this is all we need to know about this QFT. That any QFT Q with symmetry C, this could be the group-like or non-invertible, that should be finite. And we put on the boundary of this QFT. Right? But what I wrote here it doesn't make sense fully because I cannot identify a theory with a boundary theory. A theory either lives by itself or is a boundary theory. So more precisely, I should say can be fixed into a boundary condition that we call it BQ of this theory. This is the precise statement. That given any theory to the theory, I can list it to a boundary condition for this QFT, such that I can recover my original theory by reducing this theory or compactifying it on interval. So on picture, I'm putting. So I have this QFT, I put it on the interval, and on one side of the interval, I put this boundary condition. On the other side, I put some canonical boundary condition, which is, I call it Dirichlet for some, I'll explain why. It's some canonical boundary condition that always exists. And the point is that after compactification, I get my original theory. So I have a one bulk realization of my theory, and it helps me, I will explain. So, what does it mean in picture? So I just put them, any sigma, I put it on an interval, reduce to boundary condition, I get that theory. So what are the properties of this boundary condition? So this Dirichlet boundary condition. So when my symmetry is invertible, I told you that the bulk is just gauge theory. And this is literally the Dirichlet boundary condition for the gauge field. And we know that for the Dirichlet boundary condition, the gauge symmetry, the gauge group becomes a global symmetry on the Dirichlet boundary condition, the boundary. So if I have a G gauge theory here, on the boundary I have a global symmetry G. It means that on the boundary I have topological lines formed by G. And the more general statement is that topological lines on boundary, they form this C. From this non-invertible C. If I look at the state of all line operator on this boundary, I just recover this C in all the fusion relation, fusion coefficient, and so on and so forth. And that's the precise definition of this boundary condition. So it means that if I insert, let's say, 3 lines, A, B, C, after compactification, I get ABC here. So it's useful because it says that symmetry only acts on this boundary. So I have a kind of a factorization, I don't know, kind of separation between some topological degrees of freedom and the other one. So all the symmetry data, the symmetry action is captured on this boundary. And all the other data are in this non-topological boundary. And that helps me to find a asymptotic density of formula. For instance, you could ask, what is a local operator in this theory Q? Let's have a local operator O. A local operator O is a pair of 2 boundary operators. I have to pick one boundary operator O tilde and one X, but they might be connected to a bulk line. Let me call it mu. So all the local operators are given by this pair. I could also consider something in the twisted sector, add something here. So now this immediately tells me that this Balkanian labels a representation. Why? Because the symmetry only acts on this topological boundary D. So this is the non-topological boundary, this is the topological boundary. And when I act on here, I can only change this label X. So I won't touch this Balkanian mu. And that means that the Balkanian labels a representation of my symmetry or tube object.
X is not the position, it's something else.
Oh, right. Yeah, it's not a good notation. It's just a choice of for this boundary. It's choice of a topological boundary operator. I don't know why is that. Let me call it this. That is not the position. Yeah. Yeah, so that's how it is. And it helps me to derive the asymptotic density formula. I'm almost out of time. I could just very quickly just give you the example of the WZW model that you get a sense of this bulk interpretation. So consider the G level K WZW model. So this has a non-invertible symmetry, which is just given by the Verlinde lines in G level K. So what are the Verlinde lines? Okay, I could briefly explain some facts about it. One fact is that the Verlinde lines are labeled by primary, labeled by primaries of the Cardy algebra, the G level K affine algebra, or the line or anions in G level K transimals theory. So I have this set of lines. But we know that the WZW model has a realization from Chern-Simons theory compactifying on the interval. So we could get WZW model And here I put holomorphic boundary condition. So A is equal 0. And here I have A z bar equals 0. So I have the holomorphic or chiral degrees of freedom on this boundary. I have the anti-chiral or anti-holomorphic degrees of freedom here. And once I compactify this, I get the Chern-Simons theory here. But both of these boundary conditions are non-topological, and you would say this is not quite the same as that picture. What you have to do, you have to fold this theory from the middle. And if you fold this theory, these two becomes a non-topological boundary, which have both chiral and anti-chiral degrees of freedom. And this trivial defect in the middle is topological, becomes the topological Dirichlet boundary condition on the other side. And I recovered that thing. And now you could ask, how about the representation? You know, the representation of these anions. So it's known that if you take 2 copies, so the anions in the bulk are just 2 copies of C. It's just C times C bar, right? So that Q C times C bar, because I have double copies of Chern-Simons. I said that they should correspond to the bulk lines in the bulk, which are C times C bar. So it means that 2 pairs of primary should label the representation. And that's very expected, because we know that in WW model, any local operator or defect operators, it's labeled by a representation of the left Carrel algebra and right Carrel algebra. And since all these lines commute with the Carrel algebra, it's their definition that they commute with the Carrel algebra. They cannot change these labels, the left representation and right representation of the Carrel algebra. So that's why these numbers labels the representation of the field in this example. Okay, I was prepared more, but I think given time, I'll stop here.
Any more questions for Sahand?
Super nice. But so this week there was a there was a pretty big paper by Dan Fried, Telemann, and Greg Moore on exactly this topic.
Sure.
So I'm just wondering if you looked at it.
No, I looked at it. I wanted actually to cite it here, but thanks for reminding me. Yeah. There was a paper just today. So it wasn't about the asymptotic density formula selection rules and anything, but it's about this picture in any dimension. So it turns out that this fact that when you have a symmetry, you could associate it to a TQFT in one higher dimension and a choice of a topological boundary condition. It's a general fact that they provide a new definition of generalized symmetries, finite generalized symmetries by this procedure. So this part is similar.
Are there any qualifiers to your statement? It seems a bit too strong. Any 2D TQFT.
This one?
Yes.
We have a proof for it, but as I said, for the invertible case, the proof goes as follows. You do the anomaly matching. You take your QFT with anomaly omega, you do the anomaly matching, it's on the boundary of some SPT. You gauge the SPT and put the Dirichlet boundary condition somewhere. So, you put your SPT here, you gauge the SPT and terminate the spacetime here by putting a Dirichlet boundary condition. That should supposed to give you this construction. You have to verify that, putting the Dirichlet boundary condition gives you the original theory back. But you have a general proof. Yeah. But this is not a new. This is not the thing that we said. It's been mentioned before in earlier, maybe from 2 years ago or something. Sorry, the appropriate references.
Explain how to get the formula.
Yeah, if you are interested, I can spend 5 minutes, give you some idea. But
we will do that.
Or we could also, at some point, end the official part, and if it was interested.
Okay. Any other questions?
Right. No, that's thanks.